Okay, good. Okay, so we can start. I mean, Clemens' title is Lifetime of Flatband States. So please, Clemens, you can go. Thanks.
Thank you very much for the kind introduction. Also, I would like to especially thank the organizers for giving me the chance to present some of our work here in this conference. It's a great pleasure to be here. It's very interesting, and I've learned already many new things about flatbands. Now, the title of my talk is Lifetime of Flatband States. And what's really behind is like a mechanism how disorder can destabilize flatband states, and in that sense result in their effectively diffusion. Yeah, in that sense, I hope that this talk can kind of shed or give a new perspective on the interplay between disorder and flatbands and localization, as we have already seen it in a few, as it was already discussed yesterday in a few other talks. And, but here I would like to take a dynamical perspective, and therefore some part of my talk will be devoted to elaborating the method that we're using, how to describe disordered systems from a dynamical perspective. Let me also mention that this is work in collaboration with Jolie and Franco Nori. Okay, now this is the outline of my talk. So I will give a very brief introduction to flatbands. I mean, there's not much that I need to say here in this conference. I will basically use this only to locate the content of this talk, so to speak, within the broader landscape of research in land-based flatband physics. Then in the first part, I will qualitatively present this decay mechanism for flatband states that I would like to elaborate in more detail in this talk. In the second part, then I will present the method, which is based on quantum mass equations and which we dub disorder-induced quantum evolution. And then in the final part, I will elaborate quantitatively the consequences of this decay mechanism and the effective diffusion, flatband diffusion at the example of the cross-stitch model. Okay, now as a very brief and short introduction to flatbands, we all know flatbands, by definition, they are dispersionless. And this can give rise to increased sensitivity to, for example, interaction and disorder. And another characteristic feature of flatbands is that they can feature compact localized states. And also, we have seen in many interesting talks already that there can be a rich interplay between flatbands and topological aspects and symmetries and geometrical aspects in the systems. Now, this talk is about the interplay of flatbands and disorder. And this talk is not about how to construct or identify flatbands or how they are related to symmetries or topology. And also, we assume a single particle picture, so interactions are excluded. And finally, we basically restrict us to one-dimensional lattices. But I would like to advocate in some sense that I think that the generic mechanism that I discuss is easily generalized to more general situations, like higher dimensions and different lattices. Okay, then let me start by briefly qualitatively introducing this disorder-induced decay mechanism of flatband states. Now let's start with the simplest situation that we can conceive, which is just an isolated flatband. So basically it's just a chain of isolated sides. So in principle, in this case, every side constitutes or can feature a compact localized state, and also every superposition of such localized states is again a flatband state. So we look at the localized wave packet, and we know that this will dynamically, there will nothing happen. It will just be freezed. And we can see this like as a desirable feature of flatbands, that they can, so to speak, that they have this storage property that we can store quantum states. But now what happens if we add on-site disorder on our chain? Yeah, like we slightly perturb each lattice side. Then, of course, there will not happen much. This was already noted yesterday already by Professor Flach in the discussion. In particular, in real space, that nothing will change. The wave packet will keep its shape. Yeah. But of course, this other potential has an effect. It causes dephasing. Yeah. And this effect is then more easily identified if we look into the momentum distribution, because there we see that the momentum distribution broadens in time as a consequence of this dephasing. Yeah. But in the case of these isolated flatbands, there's not much more that will happen. Yeah. But the situation changes if we add to the flatband a dispersive band. Yeah. So the dispersive band, if the dispersive band is close to the flatband, or it touches the flatband, or even intersects the flatband, the latter is what we will consider in this talk, or what I will consider in this talk. Then what can happen then is that due to the broadening of the momentum distribution, eventually the flatband state will overlap with the intersection region with the intersection, and then we can, if the disorder in addition couples the two bands, then we can have a coupling into the dispersive band where the state can propagate, and if it couples back into the flatband, then effectively what we see in the flatband is a diffusion of the flatband state. Yeah. So this is basically the mechanism that I would analyze in more detail in this talk. And for this, I would like to take a dynamical, meaning a time-dependent description of what happens for arbitrary initial states and taking the disorder into account. Yeah. So the Hamiltonian that I will focus on is the so-called cross-stitch lattice. So I was happy yesterday when Malte Röntgen also mentioned this reference in his talk, because this was also like this paper by Professor Flach and Daniel and others, because this paper was also the inspiration for me to actually use the cross-stitch lattice. Yeah. Now the cross-stitch lattice, we have seen it already in a few other talks. It's basically characterized by two sublattices, and each sublattice consists of two sides. So this is the yellow here is the unit cell, and each side is coupled to all other adjacent sides with the homogeneous coupling strength, and the intra-cell coupling is independent. And we see easily that the cross-stitch lattice is actually like ideal for our purposes if you look into the momentum space Hamiltonian, because then we find that the cross-stitch lattice is actually described by exactly two bands, one flat band and one dispersive band. And the position of the flat band is basically described by the asymmetric superposition of the sublattices, and the dispersive band by the symmetric superposition. And the intra-cell hopping, the TAB, controls the position of the flat band. So now we would like to have a time-dependent description of this system, this Hamiltonian, in the, that includes the disorder average. So now let me introduce the method that we are using in the remainder, which is based on quantum mass equations, and which we call disorder-stress quantum evolution. Now, for this, let me first briefly motivate why it may be a good idea to use quantum mass equations to describe disorder average quantum systems. And for this, let's look into the double slit experiment. Now in the double slit experiment, we know we have a source that, let's say, it emits either photons or electrons or some sort of particle. And then the double slit basically creates a delocalized superposition of two wave packets. Yeah? And then we all know that at the remote screen, we get an interference pattern, and this interference pattern is a consequence of delicate interplay of the phases that are accumulated between along the different paths from the slits to the screen. But now what happens if we add a disorder potential in between the double slit and the screen? So in the case of photons, this could be some inhomogeneous phase plate, or in the case of electrons, a spectral potential. Then we will, it's probably clear and intuitive that in that case, the disorder potential, it distorts the phase relations, and as a consequence, the interference pattern is lost. But now let's look at the disorder average. So we can think of this as like we repeat the experiment many times, each time with a different realization of this disorder potential in between the slits and the screen. And in that case, we recover the interference pattern, but not exactly, but with a reduced visibility. And this is exactly what we would also obtain in the case of an open quantum system, where we say the environment observes the slits and obtains switch slit information. Yeah? And about open quantum systems, we know they are commonly described by quantum mass equations, and therefore it may be a good idea to use the same formalism to describe the disorder average systems. So let me briefly summarize some of the essential facts about quantum mass equations. Now, as I already mentioned, they are usually described to open quantum systems. So they are obtained by tracing out the environment, and then they can describe incoherent effects such as damping or decoherence. Yeah? But more generally, Limplard equations can also be thought of as being like the most general form of quantum consistent quantum dynamics that preserves the hermeticity of the state and the trace and the positivity. Yeah? And if you look at the form of the mass equation, we have like the coherent part and the incoherent part, and the incoherent part is comprised of a sum of the terms in Limplard form. And the Limplard operators can be, they describe the incoherence effects to the dynamics, and they can be in principle quite general because it's the structure of the equation that preserves the properties. Now, in our case, we don't have the trace of over the environment, but instead, this is replaced now by the average over the different disorder realizations. And so each disorder realization, we assume it evolves unitarily, but as a consequence of the averaging procedure now here in this case, we obtain incoherent contributions to the dynamics. Yeah? So, and as a consequence of this incoherent evolution, of course, we have to assume that the state will in general be mixed, even if the initial state is pure. Now, the standard case usually considered in open quantum systems is that the rates and the Limplard operators are time independent. In that case, we have the equation satisfies a semi-group property. But what can also allow for more general situations where they are time dependent and even negative. In that case, one calls this non-Markovian. And as we will see in the case of the disorder average, this will be actually the generic situation, because such non-Markovianity is required in order to find or obtain coherence revivals, as we have to expect it in the case of the disorder average. Now let's turn to like the explicit form of the equations for the description of the disorder average. So this is, so to speak, the object that we are looking at, the disorder average state. We have an initial state, and then for the epsilon parameter, it labels the different disorder realizations. They occur, each realization occurs with a probability P epsilon, and each realization evolves unitarily according to a Hamiltonian, yeah, a time-independent Hamiltonian. Now, the way we obtain our evolution equations is by decomposing the state for each realization, rho epsilon, into the average stage and an offset, and then to derive independent evolution equations for the offsets, or coupled evolution equations for the offsets and the average disorder average state. And then in the limit of weak disorder, one can obtain a closed evolution equation for the disorder average state, which is time local in the state, and which again assumes the Limblad form, where the effective Hamiltonian now is described by the average Hamiltonian and the Limblad operator and the combination of the disorder potentials, and similarly the Limblad operators are described in terms of the disorder potentials, where each disorder realization epsilon in principle gives rise to an independent decoherence term. Yeah? And because here we have the sum over alpha plus minus 1, we also see that we generically get these, so to speak, negative rates, which give rise to the non-Markovianity and hence the coherence revivals. Yeah. Let me just mention that beyond the assumption of weak disorder, this approach is quite general and can therefore in principle apply to arbitrary disordered systems and arbitrary disorder characteristics. Okay, now to see how this works, let's look at an instructive example, which is the transport of an edge state in a topological insulator. Now, we know in topological insulators, we have the topologically protected edge states, which can propagate backscattering free along the edge. And they, in momentum space, they live in the band, in the bulk band gap. Yeah. And here, now let's make like a simple assumption that the dispersion relation that describes the edge states in the gap is basically a linear dispersion. So we make this ansatz for the Hamiltonian linear dispersion, and then on top of that we add a disorder potential, which we assume to be on-site. And now we would like to understand the effect of this disorder potential, the residual effect, because we already can exclude backscattering. Yeah? Now, we have to make some statistical assumptions about the disorder potential. And for this, we introduce the correlation function, which we assume to be homogeneous, so translationally invariant, and characterized by a correlation length L. And we also introduce the Fourier transform of the correlation function, which, as we will see, takes the interpretation of a momentum transfer distribution. And we will see this in a moment. Now, this is how the disorder just evolution equation evaluates for the, in this case, yeah, for the edge state transport, the backscattering free. And now let's see how we can read this equation. Now, the first part, this is just the constant drift term, the coherent constant drift term to the linear dispersion. There has nothing changed. Yeah? And this is now the incoherent part. And here we see that now the integral over the disorder realizations is replaced by an integral over momenta. And the Limblad operators basically now describe momentum kicks. Yeah. So, and the strength or the probability for the momentum kicks to occur is controlled by the Fourier by the momentum transfer distribution, which is the Fourier transform of the correlation function. And we also have here this sinc factor, which can get negative and which already indicates that there will be some non-Markovian effects in the evolution. Now, one of the nice things about this equation that we can solve it easily, exactly in position representation. And then what we see, I mean, it's a simple system. So basically we just see this constant drift of the wave packet of our initial state rho naught. And then this term basically describes the decoherence, yeah, so the decay of the off-diagonal elements of the density matrix in the position representation. So this F bar function, this disorder effect, it vanishes on the for vanishing X, so on the diagonal. So for the populations of the in position representation are unaffected. Yeah, but the off-diagonal elements, there's something more interesting happening. For the off-diagonal elements, we basically find what we call a decoherence cone, meaning that the y-axis is now time, x-axis is the x, the position. We find that all the coherences inside the cone, they have, so to speak, ceased to decay, while the coherences outside of the cone, they are still decaying. Yeah? So, and as a consequence, so the consequence of this is that we effectively, this disorder-induced dephasing has, so to speak, a limited effect on the wave packet, depending on the width of the wave packet and the velocity at the edge. And one of the immediate consequences is that we find a bound momentum broadening of the wave packet in momentum space. Yeah? And another insightful way of analyzing this disorder-induced dephasing is by looking at the purity of the state. Yeah, the purity, it's useful, because it's like a quantifier for the effect of the disorder on the disorder average state, because it basically can be thought of like as a measure of how strongly the different disorder realizations deviate from each other. And then we find that, so to speak, the purity decays and then takes a plateau value, which is again a consequence of this decoherence cone, and which implies there's bound purity loss. Yeah, and this bound purity loss is the stronger, the smaller the V. Yeah, which already indicates that there's this pathological limit of vanishing velocity, which we encounter in the case of the flatband. And also we see that we can obtain purity revivals if we have our circular topology, like along the edge, if we return to the initial state, initial position, which is a consequence of the non-Markovianity. Before I come now to the cross-stitch lattice, let me briefly mention that we have also applied this formalism to other situations. For example, the transport in a parabolic waveguide, where we can recover the backscattering and an ongoing purity decay. So there we don't have this, or this again speaks in favor of the topologically protected transport along the edge. And this is even in the backscattering free regime. Yeah? Also, we looked at the case of the transport of two entangled edge particles. In that case, we can identify disorder prone and disorder robust classes of entangled states. And finally, let me mention the propagation of a Dirac particle exposed to mass fluctuations, where one finds, again, like backscattering, and in the backscattering free regime, disorder-induced Zitterbewegung. Okay, now let's move on to the cross-stitch model and see how we can apply the disorder-just evolution formalism to get a quantitative understanding of this decay mechanism that I outlined in the beginning. First, we have to say a few words about disorder in the cross-stitch lattice. Yeah, so we assume that we have on-site disorder potentials. So disorder potential for each sublattice, and then we basically obtain a matrix value correlation function, which we again assume that the correlations are homogeneous, so translationally invariant. And we also assume for simplicity that the correlations on the two sublattices are the same. So CAA equals CBB, so to speak. Now, an important insight is obtained if we rewrite the disorder potential in terms of our bands, the flat and the dispersive band, because then we find that basically this V minus, which couples the two bands, it vanishes in the case of perfectly correlated sublattice potentials. Yeah. Now in the following, I will use these Fourier transforms G0 tilde and G1 tilde, which we can basically interpret as like describing the intraband coupling correlations and the interband correlations or the interband coupling. Yeah. Okay, but before we can look at the evolution equations, we have to make another approximation, which we call the single intersection approximation. So here we again approximate the cross-stitch lattice Hamiltonian in the vicinity of one of the intersections, which is the one closer to the initial state, linearly. Yeah. Now, and this approximation is of course justified if we assume that basically the dispersive band is only relevant or in the vicinity of the intersection with the flat band. Huh? And another motivation for this is, of course, because we want to push our analytical analysis as far as possible, and this will help us on that. But of course, for the numerics later, we have to consider the full cross-stitch lattice model. Okay, now with this, we can look at the disorder-induced evolution equations, which here like manifest as two-coupled evolution equations for the flat band component of the disorder average state and the dispersive band component. Yeah. Now let's first look at the now the red shaded part here. This is basically the intra-band evolution of the dispersive band component. And what I want to emphasize here is basically just that this is now identical what we had before for what we looked at in the example of the propagation along the edge in the topological insulator, which is of course because here we have the same dispersion relation, the linear dispersion relation. And in the case of the intra-band dynamics for the flat band, we get a very similar expression, only for vanishing velocity. Yeah? And we will see in a minute that this has very different or drastic consequences on what happens in the time evolution. Now, before I took a look at the coupling terms, let's make an additional assumption, which is that we now assume that the dispersive band component, that we can assume that the dispersive band component is basically negligible over the extent where we look into the dynamics. This is again justified because we want to look into an initial state that is fully localized on the flat band. And then we just assume that like what happens in the dispersive band or the back coupling into the flat band is not so important. But of course, later we will focus on this back coupling as well, but this will happen exclusively in terms of numerics. Yeah? Okay, now to come back to our decay mechanism and to identify the decay mechanism that I outlined in the beginning now, more quantitatively here in terms of this evolution. Let's first look at the special case where we assume perfectly anti-correlated sublattice potentials. So the intra-band disorder potential is switched off basically. And we only obtain the coupling term to the dispersive band, yeah? And here, which is still a closed evolution equation for the flat band state, yeah? And this equation can be solved. This is one of the reasons why we do the approximations analytically, and we can obtain some understanding. And what we find here is basically that we obtain a decaying flat band state, but the term that describes the decay is momentum dependent. And in particular, if you look at the momentum dependence, now let's assume, we can assume that this G1 tilde here, we can think of it as a Gaussian, which is the width of which is basically controlled by the inverse correlation length. So if this is sufficiently narrow and the flatband state is sufficiently detuned from the location of the intersection, then we can basically assume that the decay has no effect on the flatband state, yeah, and the flatband state is preserved. That's exactly the case that we also discussed in the beginning. So here, in this situation, nothing happens to the flatband state, yeah. Now let's look at the opposite case where we have perfectly correlated sublattice potentials. So we now assume that the G1 tilde vanishes. In that case, we can neglect the coupling parts between the two bands, and we have the intra-band dynamics isolated. Now this equation, which is just a special case of the one that we had earlier for the topologically insulated, the edge state propagation, can again be solved in the same way. In position representation, we get again the disorder effect, which describes a disorder-induced dephasing for the coherences. Yeah. But now the difference now here is, in contrast to where we had the finite drift velocity, is that now we don't have this bounded momentum broadening, but we have an ongoing momentum broadening. So now this tells us, as we had anticipated in the beginning, that no matter how far the flatband state is detuned from the intersections, at some point in time, it will always eventually overlap with the intersections, and we should expect some coupling into the dispersive band. So to see this mechanism now at full work, now let's look at the general case where we have general correlations, neither perfectly correlated nor perfectly anti-correlated. And we consider two situations. One is where the initial state is basically resonant with the intersection, and the other one is where the initial state is basically detuned from the intersection. Now in the cross-stitch lattice, we have two intersections. Now, of course, we have to consider both of them. And here, in the detuned case, we just assume that the initial state is basically in the center between the two intersections. Now we assume here a Gaussian initial state, which is the blue dashed lines, and also a Gaussian correlation function. And the Fourier transform is here indicated by this green dashed line G0, the two green dashed line Gaussian peaks. Yeah? And then in the general case, as we described it earlier, we now will find that, of course, the momentum distribution broadens. And of course, now the mechanism now kicks in that we now find that in the first case, in the resonant case, the flatband state basically starts to decay immediately into the flatband, which we see here in terms of the trace of the flatband state. So the loss of probability for the particle to reside in the flatband, so to speak. While in the detune case, we see that initially the state remains stable in the flat band, and only eventually the decay sets in. And that's exactly when the broadening of the disorder-induced broadening of the momentum distribution has resulted in the overlap of the flat band state with the intersection. And we can roughly estimate this, what we call the lifetime of the flatband state, in terms of the detuning from the intersection, the flatband position from the intersection is P0 minus P1, and the correlation length, so to speak. Now, this delta here is basically just tells us like the degree of to what extent the correlation, the sublattice potentials are correlated or anti-correlated. And now we compared the analytical prediction of the disordered stress evolution equations, which are the red dashed dotted lines in the plot, with the numerically exact ensemble average over 200 disorder realizations. And for this, we use the lattice of 100 lattice sites, 100 lattice sites. Okay, now, as I mentioned earlier, we also want to look or discuss, like, so to speak, this effective diffusion of the flatband state caused by this decay mechanism into the dispersive band. And this is what we see here. Now, it's again the same two situations, the resonant and the detuned initial state. And what we see here is basically a log plot of the position distribution of the flatband state component. And in the resonant case, which is the red dashed dotted line, we see how the flatband state symmetrically, this is now the detuned case, the symmetric case between the two intersections. We see how the flatband state basically symmetrically diffuses. And in the resonant case, we see how the flatband, this is now here the black solid line and the black dashed line. We see how the flatband state diffuses directionally, which is of course easily understood because we couple into there's a preferential coupling into a specific branch of the dispersive band, and this branch has a directionality, which then imposes, so to speak, the direction of the diffusion. Yeah? Now, in that sense, we can say that here the disorder delocalizes the flatband state. And in that sense, maybe this gives a different perspective of what has been discussed yesterday. Also, for example, the talks by Professor Römer or by Thielen, a different perspective on the interplay between the disorder and localization and flatbands. So this brings me to my conclusions. Let me just briefly wrap up. I identified this mechanism for this destabilization and diffusion of flatband states, where we can say that disorder delocalizes the flatband states, which is mediated through the coupling into the dispersive bands. And to treat this, we use the dynamical description, which is based on the general formalism of disordered stress quantum evolution. And in this formalism, the disorder is treated as an incoherent modification of the dynamics. So we can think of this as, like, in the sense that disorder acts as an environment, so to speak, while the system remains unchanged. Yeah. Now, the analysis was basically based on one-dimensional lattices, in particular the Crossstitch lattice, and we focus on the situation where flatband, where dispersive band intersects with the flatband, but I think it should be clear from the discussion that generalizations are conceivable, for example, to high dimensions, or to the case where we have a parabolic band touching or being just very close to the flatband, and so on. Yeah. So that's all I wanted to say. Thank you very much for your attention. And let me finally acknowledge my collaborators, which have been working with me on this in various different directions, not only on flatbands, but also other topics. Thank you very much. And now I'm happy to take questions.
Okay. Thank you very much, Clemens, for the talk. We have immediately a first question from Tero. So please, Tero, you can unmute yourself.
Thank you. This was very interesting talk. I was very interested actually in this overall approach on how to treat disorder in sort of arbitrary lattices. And but I would actually, you didn't show how to get the usual sort of disorder limit from this. Do I understand it correctly that if you would have a single dispersive band and you would have mild disorder, would you be able to derive a diffusion equation from your quantum master equation? And would this be actually the Fokker-Planck limit of this quantum master equation? And then actually, second question, if I may, is that is there a way to calculate directly some linear response properties from your approach, such as conductivity?
So if let me try to rephrase the question to make sure that I understood it correctly. The first part was like the question if
just
if
earlier
we can use the formalism to derive a diffusion equation.
Yeah, from this quantum master equation. When you saw the first quantum master equation, how you do it, and if you would now assume weak disorder and single parabolic band sort of, and let's say, yeah, in which case you should get a diffusion equation for the density matrix.
Okay, maybe I think what gets closest probably to your question is like that when we treat the parabolic band case in the formalism, right?
Yeah, yeah,
and
that's
then
parabolic band and then around some finite Fermi energy.
Exactly, yeah. I mean, that's exactly what we are doing here. We are looking at an initial state at some finite momentum, yeah.
Yeah.
And then what we obtain from the formalism in the formalism is like the backscattering. So we can find like that in time there builds up linearly builds up a momentum component at the opposite momentum of the initial momentum. Yeah, I'm not sure if you would qualify this.
No, yeah, I'm looking at now. I mean, this is basically the semi-classical limit of transport. So you expand around some Fermi energy, and then you can write quantum semi-classical kinetic equations, which are just Boltzmann equations. And in the disordered limit, you get diffusion equations. And I guess you would actually get there quite easily by doing a kind of going to the Fokker-Planck limit. So you expand it with weak disorder, and you assume, I mean, you expand with Gaussian states. And okay, and this way you would get the regular sort of transport theory and maybe also linear response quantities such as conductivity and so on. And then, okay, I mean, you could do the same with more interesting systems like adding spin orbit interactions and so on.
Of course, I cannot promise that it will be easy to apply the formalism to like the more complicated cases. Yeah, I mean, that's the one that we have been looking at in the flatband. Yeah, and also maybe what helps to answer your question is that because of course we have this weak disorder, this perturbative assumption. So we expand in the disorder potential, and therefore effectively what we see is just one backscattering event. Yeah, so.
But okay, I'm looking for
like probably
self-consistent.
We would not recover full-fledged diffusion, yeah, in that case, yeah.
Yeah, you need self-consistent Born approximation for what I'm saying, but it's still a weak disorder potential.
And this is maybe also reflected by the fact that the formalism, we cannot expect that the formalism holds like to arbitrary times. I mean, I tried to make this point this out here, but I didn't mention it. So of course we have to expect that due to this dispersive expansion, eventually the description will break down, yeah, at some finite time. For example, we cannot use it to determine asymptotic states, yeah, as it would, for example, be desirable if you are interested in endless localization, say, yeah.
Okay. Okay, thanks.
Thank you for the question.
Next question from Sergey.
Yeah, Clemens, and can you explain again, please, what exactly is the mechanism of dephasing, and how is that in this 1D example of the, you called it the disorder-induced dephasing, but maybe it would be good to understand what is the difference between that dephasing and the disorder-induced Anderson localization. in this particular example of the one-dimensional cross-stitch model which you discussed?
Okay, I mean that. Okay, the first part of your question, if I understood correctly, it was the question was about this disorder-induced dephasing, how it comes about, right?
Well, yeah, in particular, when I compared it to disorder-induced Anderson localization, which where the states do become localized or extended or more or less extended, but still localized, and in some sense do not dephase. So what is your, how is your dephasing related to that no dephasing of an Anderson localized state? Maybe I can rephrase my
now,
question.
by dephasing, do you refer to like what I have described as the decaying of diagonal elements, the decoherence of the?
Yeah. So do you add actually something? Do you add a real dissipation channel, so to say, to your dynamical treatment?
Okay, that's
it seems you do, point, but you stressed, but you stressed it. But then the dephasing would be induced, so to say, by those decay channels and not by the disorder itself.
Okay, now I think the way I understand your question now is related to, like in Anderson localization, basically we assume it's a closed system and we have like unitary time evolution, and how can we have, how is this now here I'm discussing dephasing, and how can we have dephasing if there are,
right,
if it's a closed system, yeah. And that's of course an important point, and this dephasing that I'm discussing is basically a consequence of the disorder average, yeah, because I'm always discussing the disorder average state, yeah. But
there is no this. I mean, okay. Now let me take the perspective of Anderson localization. Sure. Well, I'm not sure exactly what I should do there, but I would say if I take an initial state located somewhere on my 1D, well, quasi 1D system, and I let it expand, it will always get stuck because of Anderson localization in one disorder realization problem. If I do now an averaging over different disorder realizations and I always start from the same point, I will still get the same result. So,
yes,
so there is no, right. So,
I mean, what you, if you hypothetically play, so to speak, this game in this kind of approach, let's assume we have a master like such a disorder-induced evolution equation, which would be valid in the non-perturbative limit to arbitrary times. So we could capture, so to speak, Anderson localization. We can pick an arbitrary initial state and give it even some momentum, and then we know what would happen. Like as a consequence of the evolution under this equation is that the state slows down and eventually comes to a halt. Yeah.
So what you basically say is that you catch in such an Anderson localization problem, you catch, so to say, the initial part of the dynamics, but not the final.
Yeah, so to speak,
I see.
Yeah.
Thank you.
I mean, we cannot, of course, we cannot reach Anderson localization because this is a non-perturbative effect.
Yeah, thank you.
Okay, we have probably still time for a quick question if somebody have. Okay, it looks no. So let's thank Clemens again for the talk.